Hello, everyone. Welcome. It's time to kick off episode 22 of Endurica's webinar series, Winning on Durability. Thank you for joining. Before we get started, a few housekeeping items. First of all, let me just say that the system is set up so that everybody's muted and your cameras are off during the webinar, but we do want to hear from you. So if you do have questions, we would encourage you to enter those into the chat at any time. At the end of the webinar, we will go through those and answer those. So please do enter those. And I'll also mention that this webinar is being recorded, and we will be sending out a link to the recording to everybody who registered for the event, so you can do the replay and share with your friends. So with that, let's go ahead and get started. We have a special treat for you today. Tim Hunter and I are co-hosting today's episode. By way of introduction for people who are Endurica followers, Tim is the founder of Wolfstar Technologies. He's based in Milwaukee, Wisconsin. Wolfstar is a consulting and engineering software company, and their superpower is getting the mission profile data that we need to design and analyze real-world product durability. Tim brings 40 years of product engineering experience, including a past life where he did product development as a legendary chief engineer at Harley-Davidson. Dr. Tim earned his PhD at Milwaukee in engineering mechanics. And I have to mention that his PhD on metal fatigue won a singularly distinguished award, the 2013 Dance Your PhD competition. So if you're curious about that and you want to see that, if you look on the right hand or left hand side of the screen, there's a QR code. If you scan that, you'll get a chance to be educated about metal fatigue in a way that you probably haven't seen before.
Thank you, Will. It's a real pleasure joining you today. The Endurica tools and Wolfstar tools are really a great power combination together, and I think we've got a really nice example to show you today. And hey, for the Wolfstar followers out there, Will is the founder of Endurica, based in Findlay, Ohio. Endurica's superpower is durability of elastomers. So if you got a rubber part with the durability requirement, Endurica has got testing and simulation capabilities that you need to get durability right. Will is originally from the Akron, Ohio area, so it makes sense he started his career in the rubber industry, working on finite element models and how to get them to do things that rubber does. He spent a decade as chief editor of the scientific journal Rubber Chemistry and Technology. Dr. Will earned his PhD at University of Toledo in engineering science. And let me just say, seeing the solar eclipse this year with Will and the team at the Endurica Users Conference was just really an amazing feat. It was just so great to be right in the path of the eclipse and to see it all right there, and it was just great. But Will, I'm still waiting for your Dance Your PhD, so you got to get yours out there so we can get your video up here too. Okay, so, but I think with that, I think we're ready to go, right, Will? Let me get right into it.
Yeah. Let's dive right in. So you want to share your screen?
All right. So today's webinar is vibration isolation and durability. True Load meets Endurica EIE. We've got this really nice example here of a isolation systems for some batteries here. So we're gonna figure out the durability of these mounts on this battery isolation system here. So what we see here, this is my little camper that I use, and this camper, like most campers out there, when you the batteries that they put on these things, from the factory, they just mount them directly to the hip, right directly to the tongue of the trailer there. Getting it from the manufacturer, the battery is getting all of the road vibration directly into the battery. And so like my battery on this thing only lasted a year or two, which batteries should last a lot longer than that. And I was really kind of disappointed. I said, there's got to be a solution here where we can isolate this thing. I worked with Marquette University's senior engineers here. This is the team that did this project as their capstone project. And they did a really nice job here. So you can see they've designed up a nice little isolation system here. They've got four 4 little stands. On top of that, they put 4 rubber isolators, connected that to a sheet metal tray that supported the battery. And then around that whole system then is the plastic battery box that protects it from the elements. So this was a really nice system. It did a nice job isolating out the vibrations. They basically did the job of taking care of the vibrations from the road going into the battery. So they really did a good job on this. But we kind of had this one lingering question: is this isolation system durable? Will it last? So that's what this webinar is going to answer here, okay? So, and for this little flat system here, so this is a little Lord isolator mount here, it'd be impossible to package a traditional load transducer on the system and have the system work as it's designed. So we chose the true load approach for figuring this out. So, our task today is to basically go through and use the true load technology to strategically locate strain gauges on that battery tray. And from that strain gauge placement, then we're going to go collect data on a route within Milwaukee here, because that's where we're located. And then from that strain data collection, our true load software is going to take the measured strain and turn that into operating loads on the structure. And now that we've got these operating loads, then we can pass those off to Endurica EIE. So Endurica can do the durability analysis on the isolators. So that's what we're going to be doing today, and we're going to kind of go through step by step on how that all works. We're going to start off here with the true load theory, though. So I just want to get you into the technology and how this the true load software works and how this is all done. So the true load technology is based on linear systems and loads. So linear systems are where loads are proportional displacements, displacements proportional strains, strains proportional load. That's a linear system, okay? At Wolfstar, we fully realize that everything in life is nonlinear, okay? We understand that. But what we're doing is we're turning your part into a load transducer. So what we're going to do is we're going to stay away from areas of high strain gradients like welds. So we'll stay away from a weld. We'll stay away from a bolted joint. We'll stay away from areas of contact. So we'll just stay out in the nice linear areas of the part where the strain response is going to be linear and proportional to the exterior loads. Now the loads could be as nonlinear as anything. They could be sinusoidal, ramp loading, impact loading. That's all okay. We just need that strain response to remain proportional and linear to the exterior loading. So I can take this little diagram here and turn it into a couple of equations, okay? So the right-hand side, well, that's F equals Kx. Hooke's law, fundamental law in mechanical engineering here. So if your structure is obeying Hooke's law on bulk, then the left-hand side of this triangle, strain times C is equal to F, has got to apply. And what we're going to do is we're going to measure forces as being strains from test times a correlation matrix from FEA. So this is what we're doing, okay? So if you looked up this technique in the research papers, this is called influence coefficients, and this equation on the right here, you'll see all over those papers. They usually don't use C, they usually use lambda, but you get the idea, it's the same thing. So here, let's take a look at this a little bit more. So we've got strain times correlation matrix is equal to load. And so on the right-hand side here, I've got 3 unit loads on my structure. And on the left-hand side, my strain matrix, I've got 4 uniaxial strain gauges. So the columns of my strain matrix, each column represents a uniaxial strain gauge on the structure. So let's walk through and see how this looks. So here, if I turn load case number 1 on and load cases 2 and 3 off, I can write down the strain responses for load case number 1. So I'll write those down, and then let's go on to load case number 2. So here I turn load case number 2 on, load cases 1 and 3 off, and now at the same 4 strain gauges, I write down the strain responses. But now these are different because load case 2 is different than load case number 1. So essentially, we're capturing the unique strain signature for load case number 2. All right. So let's go to load case number 3. So we turn load cases 1 and 2 off, load case 3 is on, and now we write down load case number 3's unique strain signature. Okay. So now we've got 3 unique strain signatures, 3 unique load cases. This is a well-behaved linear set of equations. We can solve this. This is fantastic. So let's take a look at these loads on the right-hand side. These could be anything. They could be point loads. They could be moments. They could be unit displacements. They could be pressure loads, they could be thermal loads, they could be inertial loads. They could even be mode shapes. So if you solve your structure for eigenmodes, true load would basically go through and back calculate the modal participation functions for each one of those mode shapes. So for just a handful of strain gauges, you get to understand all of the dynamics going on in your structure. So it's a super powerful way to go in and understand what's going on in your structure. So it's pretty cool. All right. So we've got this nice equation, strain times C is F, and the only thing I haven't talked about is C. So how do we find C? Well, if we look at the F matrix, if we call turning a load on a 1 and turning a load off a 0, that F matrix can become an identity matrix, and then we can do a pseudo inverse, okay? So I take strain times C is equal I, pre-multiply by strain transpose, pre-multiply by strain transpose, strain inverse, and we get C is equal to strain transpose, strain inverse, strain transpose. And that's what we call the FEM model. This is our correlation matrix. And now that we've got this correlation matrix, this is what we want to do. We basically want to go through and we want to collect time histories of strain from our proving grounds, multiply it by that correlation matrix, and that will give us time histories of loads. This is what we're doing. It's pretty straightforward and it's pretty powerful, okay? So here's our application here, okay? This is our battery tray, right? What you can see here, what I've modeled is the FEA model of stamped battery tray with a bunch of shell elements. I've got a lump mass representing the battery. It's about 53 pounds. And then I've attached that lump mass into the battery tray with an RBE3, with a distributing connector to the rest of the structure. And then my unit load cases on the structure are 4 1 kilonewton load cases on the battery tray here. So each one of these load cases is going to be activated one by one when we do the solution. And this model is being run with inertia relief. So I've got all 6 degrees of freedom of inertia relief turned on. And there are no restraints in this model. Okay, so this model is just floating in space, and I'm just pushing up on my battery tray with my 1 kilonewton loads here. Just one little note here. When I did the actual testing, I put 4 pucks inside of the battery tray that I set the battery on. That way, the battery was separated from the battery tray, and there wouldn't be any contact going on between the battery tray and the bottom of the battery. So we're not changing the flexible response of the battery tray. So I think that was a fair way to go about the testing. And because of that, then, because that's where I was resting the battery on those 4 pucks, when I set up the RBE3 is just attached to where I've got the pucks located on my battery tray. I think this is a fair way to do the FEA model here, okay? So I've got this nice little FEA model, and I solve that. And then this is what the unit load response looks like on the FEA model. So you can see the little vectors are representing the loads being applied for each one of these unit load cases. And this is being run with inertia relief. So you've got the battery tray floating in space, reacting to its loads from the unit loads being applied to it, okay? So we've got these 4 unit loads and the full strain fields here. And this is going to be the key for the true load software going forward. So as you go into the true load software here, so this is just a snapshot of the GUI, the true load software. What we do is we load in the FEA model. And once we've got the FEA model loaded in, it's going to bring in all those 4 unit load cases. And then we tell the true load software that we want to get 8 strain gauges, and then goes off and finds the strain gauges, and it draws them up here on the structure. And so this looks pretty neat here, right? So we've got these 4 strain gauges here kind of laid out on the structure where we're going to lay the strain gauges. And this is pretty much what the automatic solution gave us. I tweaked them around a little bit, but this is really, what the automatic solution gave us for this part here. So now we've got the strain gauges laid. And now the whole idea now is where you have to go do physical measurement. So we've got some nice tools with the true load software here. We can go in and the true load software will take the mesh and export that mesh to an STL file. And then we can also export the strain gauges out into an STL file as well. So we've got these strain gauges set out in an extra STL file. And so what we can do is we can go into CAD, we can import the STL file of our part, and then we import the STL file of the gauges, and we cut the STL file of the part with the gauges. And so now we've got this nice little template of where the gauges need to go. And then we can 3D print them. And my 3D printer is a little bit small, so I had to cut this part in half here so I could fit the part on my 3D printer. But you can see now I've got locations here of where the strain gauges go in my little template. And then I've also got the key mounting features here on the structure. So I've got those also in my 3D printed part. And I can just lay them on top of the metal there, and it just lines up with the holes very nicely. And I can mark where the gauges go with just a magic marker. So no measurements, 0 measurements to lay the strain gauges. So this makes laying the strain gauges super easy. Just place the template on top, mark them out, and then lick and stick and put the gauges on. So it goes really pretty quickly, okay? So these are the layout of the strain gauges on the structure. And now that I've got the strain gauges laid out, we've got to go do instrumentation, right? So we've got the strain gauges fixed to the plate, the bottom of the battery tray there, and then cut a hole in the bottom of the battery box and fish the wires out through the bottom of the battery box. And these terminal connectors here that I've got here, I'm basically connecting the wires from the strain gauges to my data acquisition wires here, and then set it all up on the trailer here. And then this is my data acquisition system here. It's a DTS Slice Micro. It's a great little data acquisition system. It can collect up to 500,000 samples per second. We're just doing 2,000 samples per second here. And it's just this little 2.5 square box. And I've got a battery, and away we go. So this is our data collection system here. And then we're just going to go in now and go and take a little drive throughout the neighborhood in Milwaukee. So basically what we did here is, this is my house here in Milwaukee here. We drove through all the alleys in my neighborhood for some rough road data collection here. These data sampling segments are set up to be 10 minutes each. We're sampling at 2 kilohertz. And so basically, when we start and stop, when we start each data acquisition, we start from a standstill, okay? So basically, we start out, we take our data collection here, and then we're at a stop sign here, we start it again, and then this is another 10-minute run to here, then we stop and do it again, and then this goes through the parking lot up here, and we do a little route there, and then start and stop again, and then we go out to drive along the lakefront. This is Lake Michigan, by the way. Stop again, and then we come back through the neighborhood again, and then this is now the final route coming back to the house. So we had six segments, each 10 minutes. That's an hour's worth of data there, okay? And we're sampling at 2 kilohertz. And then this is our strain data. So these are our 6 sets of strain data for this, and we're seeing the 8 channels of strain for each of them. So what's nice, we didn't lose any strain gauges. We don't have any dropouts going on. So this just looks, like nice strain data collection here we got going on. And then the whole point now that we've got strain data collected, we want to now turn that strain data into load, okay? So we do that through the post-test software here in TrueLoad. So basically, we load up our data file, our TrueLoad data file from pre-test that we had, and that's got the strain gauge placement and the correlation matrix built into it. And then we loaded the strain data. And in this one test, I basically ran the bulk mode version of TrueLoad, where we can put all the data file names into one data file, and it just chunks through all the tests. So it made doing this very quick and very nice. So we did that. We pushed the button, and at the end of the day, then we get these strain correlation plots. These are automatic plots from TrueLoad. Because what happens in TrueLoad, right? We're taking the strain, we multiply it by the correlation matrix to get the loads. And now that we've got the loads, we go back into the FEA model and pull out simulated strains in the FEA model, and we plot them up. So what you see here are on the horizontal axis, we've got the measured strains, and on the vertical axis, we've got the simulated strains for all the gauges, for all 6 of our loads here. So let's take a look at this a little bit deeper here, okay? So these strain correlation plots are good. It could be better, okay? But what I've done here is I've oversimplified this battery tray situation. I only put vertical loads in the battery tray, so that we've got 4 loads, which was 8 gauges. if I wanted to do a better representation of what's going on, I should have put on lateral and full raft loads. So that would have given us 12 gauges, 12 loads, and 24 gauges. But since we're only interested in the vertical loads for this mount calculation exercise, we only needed to have the vertical loads. So this is actually pretty good if we're only having the verticals loads going on, and this is what we need for Endurica. So this is still a good analysis, but I know I can do better if I put on more unit loads and more gauges. Okay. So here's the loads that we calculated. So here's our 6 events and the load time histories that we've gotten here. And there's a couple of interesting things you can see here. One of the things is that, like on this first run through the alleys here, you can see our loading ends up being pretty much in phase, which is kind of nice. But that's the only time it's in phase. For all these other things, none of these mount loads are in phase with each other. They're all doing their own thing. And the other interesting thing is that we have a lot of these mounts hanging out on the negative side of things, and the other side hanging out on the positive side of things. And so what's happening here is that this battery box is sitting there on my trailer hitch. And so it's getting road vibration coming into it, but it's also getting pushed by the aerodynamic loads of driving. And so you've got this wind load on this thing. So what's happening is that the rear mounts are being pushed down more and the front mounts are being pushed up more, like you were seeing here. So it's very interesting what's going on. It's just kind of an interesting set of plots that we get here. And then here we've got an operating deflection shape on one of our runs here. So this is a kind of a peak event for our fifth set of run of data here. So it's a very interesting thing that we can see on this whole thing. So it's great. So now we've got that. And now the whole point now is I've got these loads calculated. We run them through our CSV exporter and we push them off to Endurica EIE. Now we've got one load curve for each of the 4 isolators and there's 6 loading profiles. So we've translated that and pushed it off to Endurica EIE. And this is where Will comes in. Okay, so Will, I'm going to turn it over to you. Okay.
All right, thank you. What we get from Tim and true load is 4 load signals. In this case, we're just looking at the vertical loads. Like Tim said, we might have looked at the lateral and the fore and aft loads as well, but just to keep things simple for this demo, we're just looking at the vertical load. So we've got 4 load signals. We've labeled them left front, left rear, right rear, and you can see kind of where those are. So here I'm showing the isolator locations, right? The forward driving direction is towards the front. You can see kind of the tongue of the trailer here, right? The hitch would be up here. So we're driving forwards. And anyhow, so these are the locations. This is the mount. And our goal here then is to analyze these load cases. And if I'm the OEM, maybe I'm probably interested in which of these mount positions is the most damaging. If I'm developing the bushing, I'm probably interested in the failure mode of the bushing under actual road loads. This is all information that we can pull out of the analysis that we're going to do. Let's talk about the workflow that we're going to do for each of these 4 isolators. So obviously we start with the loads. You'll notice I've drawn these 2 red lines here. So one of the first things we do when we look through these 4 load cases is look for the maximum load across all load cases, and we look for the minimum, right? We kind of need to know the range. Now this is a single channel problem. If this was a multi-channel problem, we would do that for all of the channels, but here we've just got a vertical load. And now once I've got those loads, I'm going to use that to define the what's called a map. The purpose of the first step of this analysis is we need to convert these loads into strains on the part, right? We need to know the strain everywhere in the part. It's a little bit crazy to sort of just say, well, I'll run a finite element job because there's just way too many time steps here and it would create a job that just runs forever. If this was a metallic part, We could use kind of a scale and combine approach, linear superposition. That's how the metals people usually do it. But of course, this is a rubber part, which has material and finite straining, all sorts of nonlinearity. So we need a process, and the process we're going to use is called it's interpolation, right? So EIE, it's an acronym. It stands for the Endurica Efficient Interpolation Engine. The interpolation engine allows us to discretize the load space, and because the loads are nonlinear in the load space, we're able to sort of break this up into small domains. And it's a linear interpolation, but the domains are small enough that that we can represent the nonlinear behavior. So in order to do that, we need, like I say, a map. And we'll unpack that a little more in a slide or two. But for a one-channel problem, what the map looks like is basically just a set of pre-computed load cases, right? Here I've shown 5 load cases. In this problem, we're actually going to use 40. But these are pre-computed load states for which we have the finite element solution. Of course, to do the finite element job, we need to know the hyperelastic behavior here. First, we do our materials testing, get the stress strain curve, run the finite element job to cover from the min to the max load. That becomes our map. And once I have my map and I have my actual load signal or signals, then EIE will turn that into strains at every element on the part as a function of time. This is a huge file, but it's generated very rapidly. And then we can take that strain history and feed it into our fatigue calculation, where we do a critical plane analysis for each element, right, taking into account the crack growth and, in this case, the strain crystallization properties of the rubber part. And that gives us a fatigue life contour that we can look at. This quickly tells us what the most critical location in the part is, right? We're seeing here at the bottom edge, maybe, of the part. And then once I have the contour, I could do an even deeper dive. Maybe if I want to look at this element, I could ask, which was the critical plane? What's the orientation of the crack that initiates? I can also ask, what are the most damaging events that I should be thinking about when I'm engineering this part, so I can get rainflow count information. So this is the basic workflow that we're going to use. One thing I'll mention is that when we have the map, you only need one map. So even though we have 4 isolators and 6 segments times 24 different signals we're going to look at, we can reuse the same map from the same finite element job to basically reevaluate all of the 24 different signals to do this fatigue analysis. So that's the workflow that we're going to follow. Here's a close-up on the mount. It's a Lord 150P-18 mount. Yeah, front and side view. Just in this case, we're just looking at vertical loading. Here's the mesh that we've used for that. Because this mount is axisymmetric, we're able to reduce this from a 3-dimensional problem into a 2-dimensional axisymmetric problem. And we've discretized the cross-section here with 927 elements. We've used quadratic elements here. We actually tried linear at first, but we were seeing some checkerboarding, so we found it necessary to use the quadratic elements to get a nice solution for this model. You can see here that the red lines are showing how the inside boundary here, this is a metallic insert, right? You can see it on this image here, right? There's this steel insert. And so what we're doing is we're just using a rigid body constraint to tie that to a control node here at the center. And then there's another control node on the outside of the mount. And we've just bonded this row of nodes here right on the edge of this inside groove. So that's bonded to the plate that inserts there. Now the faces of this are free, but it's just that inside edge that's bonded, and that's the set of boundary conditions that we've set up for the mount. Material properties are very important, and of course, this rubber materials exhibit a lot of nonlinearity. And the material properties that we've used here are properties that we've published we did an SAE paper in the spring for a bushing, natural rubber bushing, and we just, for the sake of simplicity here, said let's use those same material properties. Um, and so here you can see our stress strain law. We've used a third order Ogden model to represent the stress strain curve. You can see here the fatigue crack growth rate curve of the rubber. We've used the Lake Lindley model here to define the fully relaxing behavior. And you can see we've also defined a strain crystallization effect. So as you increase the R ratio, you see a retardation of the crack growth rate. We have calibrated the crack precursor size for the material at about 20 microns, right? So basically we do a crack nucleation test, which came out at 11,000 cycles, and then we find where that intersects this calibration curve that we compute with the Endurica code, and that tells us the precursor size of 20 microns. So in other words, we're saying that in this analysis, we assume that at every point in the part, there is potentially a 20 micron size crack that can be in any orientation. And we're just using fracture mechanics to evaluate all of those possible locations, all of those possible orientations with this crack growth rate law. If you take those material definitions, you can see here on the right the syntax that we input to the code to define this set of properties. But if you take that material property set and run that through the code can compute a Hay diagram for you so you can see what that looks like. The Hay diagram is just a map that shows how the fatigue life depends on the mean strain, that's the x-axis, and the strain amplitude, the y-axis, right? So the different colors are indicating different fatigue lives. Where you see blue, that's a region where you have very long fatigue life. Where you see red, that's a region where you have very short fatigue life, and so on. So, obviously when you increase the amplitude, the life gets shorter. You can see that there's some very complex behavior that goes on with respect to mean strain. There's this region where, if you're kind of in this region right here at constant amplitude, if you increase the mean strain, you actually see the fatigue life go up to a point. Of course, if you keep increasing the mean strain, eventually the life comes back down. But all of this complex behavior is computed based on the material definition that we've set up here. All right. So the first thing that you do when you use this kind of workflow is we always like to look at the stiffness of the global part. So you can see here we've just made vertical load up, load down. In fact, you can see here we did 20 points on the load, 20 points on the load positive, load negative. And you can see it's apparently the load deflection response is fairly linear, which is not too surprising because rubber and shear often, looks very linear. And so you're seeing that at least as far as the load deflection curve goes. But, this does involve finite straining. It does involve a nonlinear stress strain response, the Ogden model. And you can see that best if you zoom in on the elements that are right at the top and the bottom edges of the part. So what I've plotted here is the max principal strain as a function of load. So this is max principal strain. This is max principal stress for those two elements. And you can see here that the response is highly nonlinear for the stress and for the strain. So it is very important that we have a process that can account for that nonlinearity. So now we go ahead and start thinking about our loads. Tim already kind of showed you these, but just to review, we've got a different load case for each of 4 different positions, right? Left front, left rear, right rear. These are recorded in a series of 6 10-minute segments. So altogether it's 1 hour. And these are the individual signals for the different conditions. So segment 1 is kind of starting from home and driving through some alleys around Tim's house. Segment 2 is kind of the red path you can see right here. Segment 3 is the blue path, which this is, I guess, a parking lot. Segment 4 is coming out here. This purple line here, I think, is segment 4. So coming up here north on the map. Segment 5 is coming down here, and segment 6 is then returning home. So those are the different load cases for the 6 segments. So now we need to now that we've got the loads, the next step is to try and get the strains for all of the elements in the part. And to do that, we're going to use the Endurica EIE tool. Again, efficient interpolation engine. To use EIE, first of all, we need to build a map. What's a map? Well, a map is a set of pre-computed finite element solutions. So here's an example of a map for a different part. This is a 3-channel map where we're indexing the part through different combinations of X, Y, and Z loads. You can see here, this is a 4x4x4 grid. So this would involve 64 pre-computed solutions. Once I've got those 64 pre-computed solutions, then I can play a 3-channel signal into this space, and I can interpolate to find the strain, right? At each of these points, I know the strains everywhere, and so, if I'm in between any of those points, I can just use interpolation to get the strain field. And that's all that EIE is doing. It's a very fast process. We've benchmarked it. It's like 10,000 times faster than a finite element model. So very, very efficient. Now, of course, this was a 3-channel example. EIE will support as many as 6 channels. So if you had 3 forces and 3 moments coming into the part, we could map that and we could interpolate that. For the problem at hand, we really only need a single channel. In EIE, when you build a map, the map usually consists of it can be one finite element solution, or it can be a series of finite element solutions. We call each solution a branch. And so in this case, our map has 2 branches. In one branch, we go from 0 load up to the max positive load. And in the second branch, we go from 0 to the max negative load. You can see here among the 4 different load cases that we're going to go to the right. The right front has the max load. And so when we do the first branch, we're going to run it out to the 684 newtons. When we do the second branch, we're going to run it out to the largest magnitude negative load, which is in this case is the right rear. And so we're going to run this out to negative 405 newtons. And what this means then, so I've got 20 increments, from 0 to 684. I've got 20 increments from 0 to 405. And that is my definition of my map. You can see here the solved finite element solutions kind of going through their motion as they go positive or negative. And that's the map. But we're able to use this map. Once we've built the map, I can use this for any of the load cases that we've generated. Now, this is just an example of the kind of strain history that comes out. We're actually going to get a strain history for every element for every load case. The strain history is going to have 6 components, right? 3 direct components, 3 shear components. If you look through these, I've put 2 histories here. We've got them for every element, but on the left, you're looking at the history for the top element here. That's element 90. So it's element 90, and the second history is for element 571. That's the bottom edge. So I'm looking at the top edge, the bottom edge. In our analyses, you're going to see that those are the 2 places that were the most critical. So that's kind of why I've just kind of chosen those as an example. But we get this for every element. We get this for every load case, and you get all 6 components of the strain tensor, and that puts us in a position now to feed this into Endurica CL, which if you take that, feed that into CL, that is going to give you the number of repeats of the entire history. So what we've done is we've taken all 6 10-minute segments. That's 1 hour's worth of data. We've concatenated all that into one big strain history, and then we've just fed it into Endurica CL, and Endurica CL computes how many repeats of the 1 hour recording does it take to fail the part. And so these are the results right here. The images are showing the fatigue contours on the cross section of the mount. You can, very interestingly, you can see that the rear mounts tend to fail at the bottom of the mount, whereas the front mounts tend to fail at the top of the mount. And I think this is maybe connected to what Tim had noticed about the aerodynamic loads causing the battery to want to tip back due to the aerodynamic loads. So very interesting there. You can also see here that the fatigue lives for the different positions are not the same. The most critical is the right rear, which comes in at about 12,000 repeats or 12,000 hours of operation. At 30 miles an hour, 12,000 hour works out to something like 300,000 miles. So pretty good durability, really. But if you were interested in, what's the most critical, it's the right rear. You can see that the other mounts are in a better spot, as much as maybe that's 4 times longer in life, 4 or 5 times longer in life is kind of the range that we're seeing. When you get results like this, it's also useful to take the worst element and then do a deeper dive to understand the failure mode. And we can do that. So if I take element 571 and element 90, one thing I can do is I can plot out we call this the life sphere or the damage sphere sometimes. But basically, this is just a map showing how the fatigue life depends on the orientation of a crack at these locations. The arrows are marking the normal of the crack plane. The solid line is the crack plane itself. And in this case, we're predicting a crack that initiates at 45 degrees, which if you think about how this part deforms, this actually makes a lot of sense, right? So as this thing is deforming up in tension, it's saying it's going to crack on that 45 degree plane here. And up here, it's the negative 45 degree plane, which again makes really good sense. So no surprises there. But anyhow, very useful to understand the predicted failure modes. We also can look at the time history. So if I want to look at what's the history of loading, we saw the strain history, but when you have 6 components, it's kind of hard to let's say understand the severity because that's kind of a 6-dimensional thing. So it's much more insightful to think about, for the particular critical plane that is identified, what was the history of tearing energy that goes into that crack. And to see that, we can plot out a parameter called CED, cracking energy density, and that's what you're looking at here. So this is the cracking energy density specific to the critical plane as a function of history for the right rear mount. On the left, you're seeing the top location. On the right, you're seeing the bottom location. And for each of these, I've marked the most critical event in the signal. So you can tell exactly what time. We could go back to those maps and we could put a point on the map and tell you exactly where in the signal the part saw its worst experience. We can also take, this is obviously time domain information. We can take this and do a rainflow count, and then we can also present this as a list of individual events, each of which has a peak and a valley. What we like to do is we like to plot each event on this chart, right? So the x-axis is just a list of the events, event 1, event 2, all the way out, to event 10,000 or whatever. And then for each event, we just draw a line that covers the range from the max to the min, right? So you can actually see the actual individual event ranges on this chart, and you can also see when it's a non-relaxing or a fully relaxing cycle. You can see that here. You can see for the top of the mount, the most damaging cycles are fully relaxing cycles, and then there's these non-relaxing cycles that are, by the way, when we make this plot, we also rank order these from, things appearing on the left are the most damaging events, and then the least damaging events are to the right. So basically for each range, we calculate an individual crack growth rate, we sort on the crack growth rate, and that's the plot in the bottom, right? The bottom plot is the crack growth rate for each of these individual events. You can see they go from the top to the bottom. The crack growth rate of the whole history is the sum of all the individual rates that we're showing here on the rainflow count chart. Very interesting to look at the difference between the top of the mount and the bottom of the mount. You can see it on the top of the mount, it's really mostly fully relaxing things. On the bottom of the mount, there seem to be a larger number of non-relaxing things that are going on. You can see here. So that's kind of interesting as well. This information is also very useful if you want to somehow simplify or defeature your signal. So for example, the analysis preserves an index to all the particular time steps that are associated with these events. And so if you want to say, well, get rid of, keep 90% of the damage, but get rid of the bottom 10%, you could look through these events, and you could find, if you integrate this, you can actually identify, and Endurica has a feature where you can identify the non-damaging parts of the signal, and you can exclude those and reconstitute a simplified signal or a block cycle signal that has the same damage content, but removes the non-damaging things. And we use the rainflow count output to do that. So that's kind of what the analysis looks like. We also probably ought to think about how much resource the calculation consumes. And so, like you saw, there's 3 parts to the calculation. First of all, you have to build your map. You only have to do that once. So that has 2 branches, 20 increments per branch. Because this was such a small finite element model, this model only took us 15 seconds to solve both branches. For the interpolation of the signal, which had 39,000 time steps with this model, that ran in 6 seconds on 4 threads. And so again, for these 2 tasks, the runtime is negligible. The long part of the process was actually computing the fatigue life. And in this case, Endurica CL, we ran it on 16 threads. And this is the runtime for all 4 parts. And that took a bit less than an hour, right? Well, what is that? Maybe 45 minutes, 40 minutes, something like that. 2,800 seconds was the runtime. Now, this can be scaled when you run on more or fewer threads. You can really scale that up or down. Here's an example of, we did some tests and showed how this scales from 2 to 4 to 8 to 16 threads. This number was for all four positions, 2,800 seconds. For one position, 16 threads, you're running at about 700 seconds. That is that's the workflow and the results for these for the mount. Like Tim said, the combination of the true load with the Endurica EIE is a very powerful combination. And in the past, these things were so hard that people just didn't do this for rubber, but now it's very doable. We've shown here that the runtimes are going to fit in the typical workflows that you need to do when you're making a real product. Get your loads, build your map, interpolate, solve fatigue life, diagnose. So that's what I've got. And we've got plenty of time for questions here.
Yeah. So Will, a part like this, if you're just sitting down and doing everything analytically, right? You would have done analytical assumptions like assuming that everything's moving together up and down at the same time, right? So all 4 mounts would have the same durability. And, getting real operational loads, you discover things like, oh, geez, there's a wind load here acting on this thing that you just don't think about when you're thinking about the part analytically. So there's really important information you get when we get actual operating loads. So
yeah, there used to be a good excuse. It was like nobody can do that, and so we just have to wave our hands a little bit. But it's not hard to do now, so there's kind of no excuse. Okay, questions. Are there actually 8 individual branches for this example? 4 rubber mounts for 2 times each? No. So there's really just 2 branches, one from 0 to the max load. So we only need 1 map because all of the mounts have the same response. The signals are different, but we just need to make sure that the map covers the worst case across all loads, both on the upper and lower end. So you have to envelope, you have to make sure all your load cases are part of the map, but once you've built the map, then you can use it for as many load cases as you like. Let's see, next question. How do you estimate hyperelastic constants for FEA if you do not know the polymer type and durometer or have material specimens for testing. So at some point you have to either assume something or measure something. A lot of times the starting point that we see is to start with a durometer. There are empirical equations you can use to convert a durometer into a hyperelastic law. That's never as good as actually making a measurement of a stress strain curve, but it's usually pretty easy to do. If you don't have a durometer, then you might be. I guess another method I've seen people use is to if you've got a part and you have a load deflection curve on the part, sometimes people will reverse engineer their hyperelastic law to get the right stiffness on the part. That's one of the reasons why I like to look at the global stiffness. Is now usually we measure our stress strain curves, but the load deflection curve and the stress strain curve, they're related to each other, and if everything's right, then those things will correspond to each other, let's say. We do have, the software does come with a materials database, but you have to be careful because even if you specify the polymer type, a given polymer can come in hardnesses from very, very soft to very, very hard. And so the polymer by itself does not specify the stress strain curve. It depends on how much curative they put in there, how much carbon black they put in there. So you do have to be a little bit careful there. I understand the first step of EIE is to generate strains from loads. Could the strains be generated more accurately by true load using the correlation matrix? I think since the measured strains and corresponding loads are calculated true loads FE, corresponding simulated strains using the same model would be more accurate. Just a thought.
So Will, let me take that.
Yeah.
So in my FEA model, there were no isolation mounts. There were no mounts. I did not model any elastomers in my FEA model. So my FEA model is only calculating loads as seen by the battery tray. So we didn't have any in our situation here. Theoretically, we could have done what's being suggested here if we had calculated if we had an approximation of the mounts in our FEA model for true load, but we didn't do that. We just had the battery tray in space. So we just calculated the loads of the battery tray. And so that's what we've got here. Now, theoretically, we could have, we're extracting the loads from the true load model. We theoretically could have extracted displacements. Maybe displacements would have been better for you. I don't know, but this is what we did. We calculated loads of the battery tray and gave them to you. Okay, so. So in our example here, we didn't have any isolators in our true load model.
Right. And the point is, that Tim's tool is kind of a linear tool. So if we had nonlinear stress strain response, that would have been probably difficult for if we were trying to make the direct application. That would have been hard to reach, maybe.
Well, the mounts were linear for displacement, right? So force displacement. So
if you looked at the global response, they were linear. If you looked at the strain versus load, they were pretty highly nonlinear.
Yeah. So
yeah.
I mean, the beauty of this is that I don't have to know what the mounts are, right? If I want to get the loads, I just instrument up a metal part and say, here you go. So that's the beauty.
Well, and I think that's one of the powerful things about the combination of true load with what are the loads on the mounts. And you can't strain gauge a rubber part. So strain gauging the place where the loads go into the part, that's brilliant. And not having to have some kind of, special transducer, that isn't going to fit or that's going to change the load path. That's all really, I think, game changing. Let's see. Here's another question. Could displacements using accelerometers be used to determine the isolator strain as an alternative to the load input, which was measured indirectly with strain gauges? What are the trade-offs between load versus displacement-driven fatigue analyses?
So let me take this too, if you don't mind, Will. So using accelerometers for structural analysis is actually fraught with lots of problems. So there is usually lots of huge displacement drift that happens when you use an accelerometer. So if we had an accelerometer at the base of this battery tray and you ran it through a structural analysis, you would end up having huge amounts of drift. Okay, you just get drift with accelerometers. And yeah, you could probably do a high pass filter and try to take out some of that stuff. But now you're starting to approximate the signal. And I think we've got some low frequency content that is actually really important to our part here. So accelerometers in general are problematic for doing structural analysis. They're good for kind of understanding how parts are moving relative to each other and those types of things. But if you want to do structural analysis, the structural response of a part is really the strain is what's happening in the strain response of the part. Okay, an accelerometer is just measuring an acceleration at one point on the part, and if you put a bunch of accelerometers on, you'd get all sorts of different accelerations. And so the idea is that we get the structural response through strain, and that is directly proportional to the load. And so that's really what we want to understand. We want to understand loads in the part. And accelerometers, they kind of don't tell you that. Okay, so really what we really need to use is we use new strain gauges to understand what's going on there. So
One
I'm
last
a big
question.
fan of strain gauges, not a fan of accelerometers.
So could you go back to true load after testing and add a wind load case to improve the strain correlation?
Yes, we could. So we on our battery model, I could have put an additional 4F load, let's say operating straight through the battery CG, and that could have been an additional load case, and that might have given us some refinement of what's going on. That might have been an interesting thing to do. Yes, because I didn't think about it at advance. So that might be an interesting thing to go on the back end and try that. Yeah.
So you said you chose quadratic elements, but the fatigue life is still computed in a single material point per element, the centroid. That's correct. Why do you prefer the centroid instead of the integration points? Yeah, good question. The Endurica solver obviously would be happy to run these calculations on the integration points. When we designed our strain export tools, we made the decision to export only on the centroids. Our feeling was that if you're looking at a scale smaller than the element level, that if you want to look finer than that, you should refine your mesh. And the other reason is that if you do the integration points, in this case, you multiply your compute time by, for a 2D element by 4, for a 3D element by 8, and we didn't feel that the extra computational cost was worth it. So that was a choice we made. But if people do want to do that, it is possible to do, and talk to us and we can show you how to do it if you want to. Let's see. Next question is, I'm interested to explore the workflow of EIE followed by CL. Can you share any sample tutorials regarding the same? Yes. I guess what I would say is, if you want to do this, then if you're a current user, then reach out and we can do that through a support channel. If you're not a user, we can probably get you a trial license. So give us reach out via email and we'll get you a trial license and we can work through that. I'll also mention that in about a week and a half or so, we're going to be running our simulation workshop where we're going to teach all the workflows, and we've got examples that we'll run through in class. So if you want to do some training, reach out to us and we can get you signed up. Go to our website and get signed up for the class. Let's see. How many load channels are supported at a time through EIE? We can do 6 channels. So you could have 3 forces and 3 moments. They could be displacements, rotations, moments. Anything that you would apply as a boundary condition can be added as a channel to EIE. But yeah, here we did 1 to keep the story simple. But you can do 6 channels. Tim, this one's for you. How did you collect the load from the strain gauges, then correlate the FEM model?
The TrueLoad technology identifies the strain gauge locations from the FEA model, and then basically, if you're believing your FEA model and you're believing that the linear elastics of the FEA model are working great, you can go straight from there. But if you want to do a calibration exercise, you're open to do that. And so, for example, what we do sometimes when we calibrate the model is we'll hang a dead weight on something, and then we know the input load. And then sometimes we have problems with strain gauge placement. So we've got tools in our software where we can reverse engineer the strain gauge placement virtually and maybe move them over a couple of millimeters because you had them in the wrong location. That happens occasionally, but for the most part, and really our customers for the most part, they take the strain gauge placement and go because their FEA models are working well, and so if you believe that an FEA model can solve F equals KX, then you're good. Okay, so
let's see. Does the TrueLoad work with Abacus, ANSYS, Nastran, Hyper? What codes does it work with?
we are software agnostic. so a big part of our TrueLoad software is we buy an API from a third party called CE-Tron. Now they're owned by TechSoft 3D. And basically, they provide the interface to all of the major FEA softwares out there. So basically, if it's a major FEA software, we can read in the results. And the TrueLoad technology, we're just looking at the results database. So basically, you just have to do an FEA solve, and then we'll look at the results database and go from there. So
cool. On the Endurica side, we currently support Abacus, ANSYS, and Mark, and we also have a couple customers who have their own in-house codes that we've built interfaces to. It's not hard, but that's kind of our current footprint. Let's see. Here's another question. Can you please recommend a book to handle these topics best? What I would say is probably the Endurica user manuals are probably the best place for our workflow. But if you want to sort of start to learn about the basics of rubber and fracture mechanics and the theories that we've built our tools on, there's a book by Gent, Engineering with Rubber, that I would highly recommend. I don't know, Tim, if there's a book that talks about
what we're doing, actually, there's some PhD dissertations that are really good to look at. So
Yeah.
if you want them, we can reach out to us. We'll get you those. So yeah.
So here's a question. How does TrueLoad calculate optimal strain gauge locations on complex structures?
We're looking at the strain fields as a result of those unit load cases. Okay, so you saw in my deck, I showed you the four sets of strain fields. And so what's happening is that correlation matrix has got this inverse in it, strain transpose strain inverse. And what we're doing is that we take a look at that inverse, and we don't want a poorly behaved inverse. And so we recognize the inverse of the matrix is the cofactor of the matrix divided by the determinant. So the thing in the bottom of the determinant, we're basically going through all of the strain results on all of the load cases in the FEA model, and we're maximizing the determinant to strain transpose strain to find us the strain gauge locations. And it works really quickly. And what's really interesting is that when you look at the strain gauge placement, it's basically placing strain gauges on the primary load paths in the structure. Is every time I do it, it's like I look at it's like, wow, yep, the load is flowing right through there. So it lays it right in the primary load paths of the structure. It's really kind of neat how that works. So
we'll do one more question. How to validate the strain correlation is acceptable or not? Is it just a visual judgment?
Well, we do these strain correlation plots like I showed you in mine, and that's the tool. So you're looking at those strain correlation plots, and typically on properly set up models, we get that strain correlation within 2 to 5%. And if your loads are getting your strain response within 2 or 5%, you got the loads right. That's really what it is. Okay.
Well, that's all the time we have for today. So we'll go ahead and close it off there. I'll just mention that I've got a class on using the Endurica tools coming up in about a week. We'll talk about CL and DT and EIE and how to use the Endurica tools to do fatigue analysis. So if you're interested, shoot us an email or check out our website. That's there. And otherwise, thank you. And
one more thing, right? This is recorded, so we'll follow up with everybody with the recording, right?
Yep.
Okay. Great. Thank you.